everyone. This video is about enantiomers. That's the last type of isomer that we're going to learn about this year. These ones are even more the same than we saw with the cis-trans isomers. Similar to the cis-trans isomers, the molecular formula is the same and the structural formula is the same. So that means they'll have the same chemical properties. Whenever the structural formula is the same, the chemical properties will be the same because all of the functional groups are the same. And similar to cis-trans, it's the shape that's different, but it's a different way that it's different this time. This time it's not a double bond, it's just a carbon, but the carbon has to have 4 different groups around it. Okay, so if we've got a carbon with 4 different groups around it, this tetrahedral shape is really important. So I've got one and it's got 4 different colors to represent the 4 different groups. They can be anything, the 4 different groups. And so I'm just got like a red color here. That could be any sort, and I'll give you some examples in a minute. And if there are 4 different groups, then there are actually 2 different ways of making this. You might think, oh, well, green, blue, red, gray. That's it, right? But what about this one? This is green, blue, red, gray as well, but they're not the same. If I try to put them on top of each other, with the greens together and the blues together, now the red and the gray are opposite. So that's kind of like our hands. Our hands are the same, but they're not the same. We have a left hand and a right hand. And that's often how these are described as well, as a left and a right form. Now, if 2 of the groups are the same, if this was red and red instead of red and blue, then they are the same. We can't make them different by putting groups in different places. So they do have to have all 4 groups to be different. And there are a couple different names for that: asymmetric carbon or a chiral center. So why does this matter? Why are we worried about this? Well, it's even more the same than cis-trans. The physical properties are the same. Okay, so the melting point's the same, the boiling point's the same, the density's the same for these 2 enantiomers. There's only one physical property that is different, and it's related to light. It's how they behave around light. And when light is passed through one of the enantiomers, only one, then the light will rotate in one direction. If it's passed in the opposite enantiomer, then the light will rotate in the opposite direction. This is kind of a weird idea, so I've got a little video that hopefully will make it a little bit easier to understand.
Okay, first we need to know about plane polarized light. The light on the left is just regular light. The oscillations are all over the place. But if you pass it through a plane polarizer, the black bars represent that, then you're left with plane polarized light, which is coming out on the right. This oscillates in only one direction or one plane. Now, once you have this plane polarized light, if you pass it through one of the stereoisomers from a pair of stereoisomers, then it will rotate the light coming out by a certain angle. And if you pass it through the other stereoisomer from a pair of enantiomers, it will rotate it the other way. And so a polarimeter detects these rotations and can identify the isomer you have.
Okay, I hope that video showed it, at least as well as I can with my little hand gesture. So light is normally a mixture, is going all different ways, and so the polarizer lets us rotate it. It actually does rotate all types of light, but the only way we'll see that it's rotating this light is if it's plane polarized. Otherwise, it's all just random and it still kind of looks all random. But if we polarize the light, then we can see this rotation. It's not changing, it's not coming out at a different angle. Some of you will know that things can do that, like water can do that. This is different. It's still going in the same direction, but now it's rotated the wave, but it's still coming right towards you. And so That's a weird thing. We can make use of this. We can identify which enantiomer we have, like they said in the video. If we know that something is just one enantiomer, we could know its concentration of a solution or a gas. So it can be useful to know this property, but really it doesn't seem like that important a thing to us if it doesn't change its melting point or boiling point or density or anything. But there is a really important reason that we do care about this. We care a lot because we are biological systems, and those of you who study biology, you'll know that enzymes work by chemical molecule shapes. And so one enantiomer will react in a body, in a biological system, differently than the other enantiomer will. And there's a really famous example of this, and it's called thalidomide. So here's the thalidomide molecule, and it's got this one carbon right here that has 4 different groups around it, and you can have the R form or the S form. And you can think of that as like the right-hand form and the left-hand form. And you might think, well, what difference? Well, in our bodies, it makes a huge difference. One of them is perfectly safe, and the other one actually causes problems, especially in babies growing inside a person's body, a woman's body. So yeah, in the 1950s and 60s, so a long time ago, they didn't test drugs as well as they do now. And sometimes we find that frustrating that it takes so long for new drugs to come out. But this is one reason why, and this is a good reason why. They didn't test it so much, and they didn't know that it had this effect. And many babies were born, and many people are alive now who were affected by this. And it prevented the growth, it prevented the normal growth of their arms and legs. And if you go onto the internet, you might be able to find some of these images as well. So many people at this time were born especially without arms. And you can imagine that made their lives much more difficult. They still managed, many of them, to do amazing things, but it was much more difficult than it might have been otherwise. So although there's only one physical property that's different and the chemical properties are the same, the biological properties are not the same. I'm not going to ask you on a test to give this example, but I hope it helps you to understand why we're learning about this weird thing. Although the only thing that it does chemically is one of its physical properties in a chemical sort of sense is how it affects light. It can rotate the light, but really the reason we care about this is because what does it do to us? So that's the last type of enantiomer, and we'll do some practice drawing the shapes and looking at some examples when I see you. Bye-bye.